This is the first lecture for Chapter 11, which deals with alkanes. In this presentation, we will be covering the following: hydrocarbons. So we'll define hydrocarbons and we'll discuss that. Then we'll look at alkanes. So we'll define alkanes again. And we'll look at the sources of alkanes. We'll also look at the structure of alkanes. Then we will look at how to represent the three-dimensional atomic arrangement of alkanes. We'll look at isomers next. Remember, isomers here have the same formula, but different connectivity. And lastly, we'll look at nomenclature. How do we name alkanes? Okay, so let us start. As we said, hydrocarbons, as we indicated earlier in the previous chapter, hydrocarbons are really organic molecules that contain only carbon and hydrogen. So notice no heteroatoms. So remember, heteroatoms are atoms that are not carbon or hydrogens. They're like oxygen and the halogens. But in this case, hydrocarbons are now defined as organic compounds that contain only carbon and hydrogen atoms. As we mentioned earlier also, there are literally millions of different organic compounds. And there are literally millions of different hydrocarbons. So to study the different hydrocarbons, as scientists, what we do is we put these into categories that have some similarities. And then we study these categories. So of the broad number of hydrocarbons, we can break them down into classes or categories. One is alkanes. That's what we'll cover in this chapter. And alkanes, as you'll see here, are carbons that have 4 bonds to it. So carbons that have 4 bonds, all single bonds. Keyword here is single bonds. In the next chapter, we'll do another category of hydrocarbons that's called alkenes. Notice the E. And that's because it has at least 1 carbon-carbon double bond. Then, in chapter 12, we look at alkynes. Notice the Y. That's different from alkenes and alkanes. And in this category, we have carbon-carbon triple bonds here. As you can see, here's a carbon-carbon triple bond. And in chapter 13, we'll look at molecules that contain double bonds and single bonds in a ring, such as benzene. But for this chapter, or the next 2 lectures, we'll be looking at alkanes, hydrocarbons that are made up of carbons and hydrogen that contain only carbon-carbon single bonds. So, natural gas is an example of alkanes. Natural gas is made up of, as we've seen here, about 90 to 95% methane. We haven't learned the nomenclature yet, but that's CH4. That is the formula for methane. It also contains about 5 to 10% of ethane, which is C2H6 or CH3CH3. It also contains other hydrocarbons that contain at least 3 to 4 or 5 carbons, such as propane, 3 carbons, butane, 4 carbons, and of course methyl or isobutane, which contains 4 carbons. Petroleum is another example of alkanes, and these are more viscous and heavier compounds, typically your kerosene or your tar, etc. As you can see here, they're from the decomposition of marine and animal life over a long period of time. So how do we obtain these different hydrocarbons from the fossil fuels? So it's done primarily by distillation. So here we would have here the petroleum from the ground that's comes from the ground or mined from the ground, and it's heated. And of course, what we have here is a distillation or fractional distillation column. So as this is heated, it of course evaporates and goes up through the column. As you can imagine here, the one that rises to the top would be the hydrocarbon with the smallest number of carbons, such as C1 to C4, the methane and the propane, etc. And different regions in the column would be your heavier. So your gasoline would be next from the top, because that's made up of hydrocarbons from C5 to C12. And of course, kerosene is next, and we have the others down here, such as lubricating oil, which is really thick and viscous and remains at the bottom. So this is essentially what's done in industry. This gives you a picture of what's seen if you look at an distillation chemical plant. You'd see a long still, which is basically that fractional column. And it's heated down here, and of course different fractions come off here. You notice over here though, there is a flame. So if you look at most of these chemical companies that do refinery, you notice that there is always, or typically, a flame, and that's coming from the light hydrocarbons, the methane and the propane and the butane that's being burnt off as it comes off. So that's basically how hydrocarbons are obtained from the fossil fuels. Okay, let us look now at alkanes and the structure of alkanes. So as we mentioned, alkanes are hydrocarbons that contain hydrogen and carbon. Key here though is that the carbon-carbon bond, they are all single bonds. So there are no double bonds in an alkane. The two simplest alkane would be methane, CH4, and ethane, C2H6. That's shown here. So here's methane, CH4. And what you may want to do here is to use your model set to build this molecule, methane. You will see the geometric arrangement of the atoms. In other words, it's not a flat molecule, but it's described as tetrahedral. So that is what we're trying to draw here, and this is what we're trying to represent here, the three-dimensional arrangement of these molecules. Here's ethane. Here's the three-dimensional arrangement using the model. Looks a bit funny, but we can draw it looking like this. But you should know that this is really what it looks like in 3D. Let us look at a little more complex molecule here. So let's look at propane, for example. So this is propane, carbon number 1 with 1, 2, and 3 hydrogen, carbon number 2 with 1, 2 hydrogens, and carbon number 3 with 1, 2, and 3 hydrogens. Notice there are 4 bonds to each carbon. This carbon, for example, has 1, 2, 3, and 4 bonds. to it. So here is another way of representing it: CH3, CH2, CH3. Here, however, is another shortcut way of representing the same molecule. We call that the line angle formula. So look out for that word, line angle. What is done here, instead of drawing out all the hydrogens, we just use a line at the intersection to represent a carbon, and since we know that carbon has 4 bonds to it, what's not shown would be the hydrogen. So let's look at this one, for example. Here is a carbon, and it's right here. Notice there are no hydrogens shown, but we know that there are 3 hydrogens bonded to this carbon. But we do not write the hydrogens in whenever we write the line angle formula. Here is a carbon, and here is that carbon. No hydrogen shown, but we know that there are 2 hydrogens. Why? Because there are 4 bonds to a carbon. Here is 1 bond, here's 2 bonds, so the other 2 will be bonded to hydrogen. Here is another carbon over here, and this is it right here. It has only 1 bond to that carbon, so the other 3 bonds would be to hydrogen. So in the line angle formula, the hydrogens are not drawn in, only the carbons, and they are represented at the intersection of a line. Let's look at this one, butane. So if given this, can you tell that it's butane? Let's see. Here the line starts. We know that's a CH3. Next we have an intersection here with 2 lines to it, which means that this is a carbon that's bonded to a carbon here and to another carbon here, and there are 2 hydrogens here. There are also 2 hydrogens here, and there's a carbon here with 3 hydrogens. So you should be able to utilize the line angle representation or formula and determine the chemical formula, or how many carbons and how many hydrogens. Let us see, as a last example, let's look at this one, for example. So let's do the analysis. Here is a carbon with 3 hydrogens. Here is a carbon with 2 hydrogens. Here is a carbon with 2 hydrogens. Here is a carbon with 2 hydrogens. And here is a carbon with 3 hydrogens. So again, we will be using this representation a lot throughout our course in organic chemistry. Why? Because it's much easier to draw, and as chemists we understand what the structure represents. Let's look at a couple more examples. So here is the line angle of a molecule. Let's see if we can understand what this means. Here the line starts. We know that's a CH3. It goes here. So here's a carbon that I'm highlighting here in red. But this carbon has 1, 2, and 3 bonds to it. So therefore there is a hydrogen right here to make the 4th. Here's a C with 3 hydrogens. Here's a C with 3 hydrogens. So this molecule here has 1, 2, 3, 4 carbons, and it has hydrogens. So let's add them up to see what we get. 3, 6, 9, and 1 makes 10. So that would be the chemical formula for this molecule as represented using the line angle structure. Let's look at this alcohol. So again, CH3, CH3, H, one hydrogen because there are 3 bonds right here to that carbon. Here's a CH2. I should point out that in the line angle, if there's a heteroatom, as shown here, we put the hydrogen in. But if it's just a hydrocarbon, we do not put the hydrogen in. Okay, let us look at a couple more examples before we leave this. So here is the line angle for this molecule, and here is the line angle for this molecule. So now let us look at constitutional or structural isomers. So let's first of all define isomers. Isomers are molecules with the same chemical formula, but they have different structures. In other words, for hydrocarbons, the carbon-to-carbon connections are different. So let me repeat that. So isomers, by definition, are compounds that have the same molecular formula. Same number of carbons and hydrogens if they are hydrocarbons. But the connectivity between the carbons is different. Here's a classic example. C4H10 that we looked at earlier. So we can write C4H10 as this. I hope you recognize that C4H10. Let's just make sure. CH3, CH2, CH2, CH3. That is C4H10. We can also write C4H10 like this. CH3, CH, CH3, CH3. That has the same molecular formula, but notice the connections between the carbon atoms are different. So these two molecules are isomers. To be more specific, they are constitutional or structural isomers. Now, the term that's used primarily in this text is constitutional isomers, but you may see also structural isomers. Same definition. So these two molecules here, they are isomers. They have the same formula. However, the carbon-to-carbon-to-carbon connection is different for this molecule compared to this molecule. Therefore, they are called constitutional isomers. You should be able to recognize constitutional isomers. As you can imagine, based on the number of carbons, the number of constitutional isomers increase rapidly. So for methane, which has 1 carbon, there's only one way you can write that. You go to C5, 3 ways, 3 constitutional isomers. C10, 75, and it jumps exponentially after that. Look at that. If you have 30 carbons, you have this many different possible ways of writing the carbon-to-carbon connections, constitutional isomers. So let's see if we can apply what we've just learned. So, for the formulas shown below, are they the same or are they constitutional isomers or structural isomers? So let's look at this. This one, is this the same as this? So as scientists, you'll have to have a systematic method to analyze that. So let's see. We say that the connections should be the same if they are the same molecule. And the carbon-carbon connectivity, if they are different, then they are isomers. So let's look at the connectivity for these two molecules. Carbon to carbon to carbon to carbon to carbon to carbon. Let's look at this one. Carbon to carbon to carbon to carbon to carbon to carbon. It's just drawn a little differently, but the connections seem to be the same. Let's look at this one, however. This molecule here, question is this molecule the same or different, or are they isomers? Notice the formula here for both is the same. So you'll have to determine the connectivity. Are they different or are they the same? This one connects to this, and here is a carbon. And then this carbon is connected to this carbon. But look at this. This carbon is connected to this carbon, and there is not this carbon down here. So it's telling us that the connectivity could be different. So let's look at the answer, which is on the next slide. So as you can see here, these are the same compound. This molecule is the same as this because the connectivity is the same. However, these are constitutional or structural isomers because, as we said here, the connectivity are different. There's no methyl group connected right here. So you have to be able to look at molecules and determine if they are the same or are they different. Let us look here at drawing molecules using the line angle representation. So let's look at constitutional isomers for compounds with this molecular formula. So this is a loaded question. Can you draw constitutional isomers or structural isomers with this formula? So what we're asking you is essentially what we did on the previous two slides. Can you reverse your thinking and now apply that differently? So here we have C6H14. So can you draw two different molecules that have the same molecular formula C6H14, but the structure will be different? Let's see. So we have C6H14. Using the line angle representation, we can draw 6 carbons in a straight line. So this represents here C6H14. Just to remind you, the hydrogens aren't shown, but this is CH3, CH2, CH3, CH2, pardon me, CH2, CH2, and CH3, because there are 4 bonds to each carbon. This formula here is the same chemical formula C6H14. However, the connectivity for the carbons for this molecule is different than this molecule. Let's see. This carbon is connected to this carbon, but there is another methyl group connected to this carbon, and this carbon is connected to this, this, and that. So this now has 5 carbons in a line, and one we could describe that as a branch to that straight line. So this molecule here is C6H14, same chemical formula. However, the structure is different. So therefore, these two are constitutional isomers. Is there another possibility? Yes, there is. There are other possibilities. Here's another one. This is connected to this carbon and to a third carbon. However, now we have a methyl group on the third carbon. So therefore, this molecule here is different from this molecule here. because the connectivity, the carbon-carbon connectivity is different. Let's look at this one. Now we can have 1, 2, 3, and 4 carbon in a straight line, and then we can put 2 methyl groups or 2 groups that contain just 1 carbon here, 2 CH3s. The connectivity for here is again different than here. And here's another possibility as shown here. Same 4 carbons, but now we have a CH3 here and a CH3 here on different carbons. So this is a good exercise to expand your thinking and your observation. Can you look at molecules and determine if they are the same or are they different? This is extremely important in especially biological and pharmaceutical chemistry, because the body can detect these different isomers as different. In fact, one can be poisonous and the other one can be the one that actually is good for the body. So as scientists, we should be able to apply that reasoning, that observation, to determine if molecules are structural isomers or are they the same. Okay, let's turn our attention now to the naming of organic chemistry. We have a fancy term for that, and we'll call that nomenclature. And this system of nomenclature was designed or determined, initiated by the International Union of Pure and Applied Chemists. So we'll just use the acronym IUPAC. So that's the IUPAC systematic naming of compounds. And why do we need this? Because we have chemists all over the world, and chemists are constantly communicating to each other. So it becomes important to have one language. And the language of nomenclature was determined by the IUPAC group years ago. So as chemists and scientists, let's see if we can learn this systematic way of naming compounds. First, if it's a straight chain, here are the names given. So if it has 1 carbon, the name is methane. So CH4 is methane. So now you can see why we just said methane, and we all understood it's CH4. If it had 2 carbons, it's ethane. 3 carbons, 1, 2, and 3, that's propane. And 4 carbons, 1, 2, 3, 4. Notice this 2 here means that this is CH2 times 2. That's butane. 5 carbons, pentane. 6 carbons, hexane. And we'll just go to 7. 7 is heptane. So let's do one more. 8 carbons is octane, because that's important for the fuel industry. So what I want you guys to do is to really, memorize, but have available this chart whenever you write the IUPAC names or ask to write IUPAC names, because you will make reference to the number of carbons and the corresponding name: methane, ethane, propane, butane, pentane, hexane, heptane, and octane. So look out for that. So let us see if we can apply this. So here is a molecule. It has 1, 2, 3, 4, 5, 6 carbons. 6 carbons. Right? And it's a hydrocarbon. It's a straight chain. It has 6 carbons. So looking back at this, 6 carbons here is hexane. So therefore, the name of this molecule here is hexane. So you should be able to name molecules based on the line angle representation of these molecules. Let us look at isomers. How do we name isomers, or molecules that have branches onto that straight chain? Okay, so we'll call this branched alkanes. How do we name, what is the IUPAC name for branched alkanes? Remember, alkanes here are hydrocarbons that have carbon, hydrogens only, and carbon to carbon single bonds, or 4 bonds to a carbon. So let us look at this molecule here. How do we name that using the IUPAC system? And it says first we have to identify the longest chain. Notice here the longest chain. So let's look at this molecule. Notice this is used here using the formula, and this is the line angle formula. So the longest chain would be here, 1, 2, 3. 1, 2, and 3. Or as you can see here, this is 1, 2, and 3. So we number it. Carbon number 1, carbon number 2, carbon number 3. Why do we number it? Because this 3 here will tell us a starting point for the name of that. That's 3 would be for propane. So notice propane. So that's part of the name. 3 becomes propane. However, it's not just propane because it's not a straight chain hydrocarbon. It has a branch which has 1 carbon. 1 carbon, as you'll see from the table that we had before, is a methane. So we'll change that methane to a methyl, THYL, and combine that so we have methyl propane. We have to indicate the position of this methyl group here, and it's on carbon number 2. So that's why we have a 2. So again, we identify substituents. We call this group here substituent or a branch by a name based on the number of carbon, and by a number which is the position of that group. Okay, so let's see if we can apply that to another example over here. Well, before we do that, so just want to emphasize here, if it's 1 carbon, instead of saying methane, it's going to be a methyl, and so on. Okay, let's apply that here. So in definition or in observation, here's a molecule. So we have written it 2 ways here. One way is here, and the other way is using a line angle. I hope you can see that the line angle is a much quicker and easier way to draw these molecules. So I'm hoping that you can visualize this by just looking at this line angle structure over here. So let's look at this. So we have the longest chain, which is right here, 8 carbons. Or if you look at the line angle, the longest chain is right here, 8 carbons. We have to number them. 1, 2, 3, 4, 5, 6, 7, 8. So it's best to number it. Why do we number it? Because we know that 8 represents an octane. Right? We know that on carbon number 4 there is a CH3. Remember, this is a CH3 because it has a carbon here that has 3 hydrogens. Because it has 1 carbon, it's a methyl, so it becomes a methyl octane. Notice we're combining the names here. That's the thing about IUPAC naming. We tend to combine, well, we don't tend to, we combine the different portions of the name to get a really long, complicated name at times. But if you analyze it, you can see that it's made up of different parts. And of course, it's on position number 4. Okay? All right, let's look at another example here. So the question is, what is the IUPAC name of this molecule here? More than likely for the quiz and the exam, we won't give you this structure, but we will give you this structure, the line angle. Why? Because it's so much easier to draw. And as chemists, that's how we communicate, using the line angle representation. Let's look at this. We can number this. We can do 1, 2, 3, 4, and 5. However, the rule says we have to start numbering from the end closest to the branch. So here's a carbon, and it has a branch right here, so we'll number in this direction and not the opposite. So once again, if there's a branch, start numbering at the end closest to the branch. So you do not start here, don't start here, but you start over here. Why? Because this branch is closest to that starting point. So the numbering will be 1, 2, 3, 4, and 5. And as I pointed out earlier, why do we do this? It's because chemists all over the world, we have to communicate with each other. So we have to abide by the rules so that we can communicate effectively. So for this, it's 5 carbons. 5 carbons represents here a pentane. 5 carbons represented pentane. We have a CH3 group. CH3 is 1 carbon, so it's a methyl pentane, and that methyl group is on carbon number 2 here. Notice not 4, because we have to start from the end closest to the branch. Okay, let's look here at another example. So here is a molecule. This is, of course, the formula using the indicating the carbons and hydrogen. But as we said, we prefer this one over here, the line angle formula. Much easier to draw and much easier to communicate with each other. So let's see. Here we have 1, 2, 3, 4, 5, 6 carbons. But the question is, do we start numbering here or here? You can see we won't start here because this carbon number 1 has a branch right here. So the numbering goes in this direction. Okay, so on this one, it's 6 carbons, so it's a hexane because of 6 carbons from that table. Here, however, we have a methyl group, CH3, and another CH3 on different carbons. They are on carbons number 2 and carbon number 4. So as you can imagine, it could be written as methyl, methyl, but instead we combine that and we say it's a dimethyl, 2 methyls. Of course, we'll have to indicate the position of those 2 methyls, and it's on carbon number 2. Here it is. And carbon number 4. Here it is. So again, so the IUPAC name of this molecule here is 2,4-dimethylhexane. I should point out the numbers are separate by a comma. Make sure you write that in. And numbers and letters are separate by a dash. So let me clear that so you can see it. So again, numbers are separate by a comma, and number and letters are separate by a dash. Very important in the nomenclature of organic compounds. Let's continue with the rules. So let's look at this molecule. So here is the molecule showing all the hydrogens and the carbons. And of course, here's what we prefer. Here is the line angle. So we do the longest continuous chain. And here it is. 7 carbons. So we know that will be heptane. heptane. And we can start here or here because the branch is on carbon number 2, number 3, or number 3, starting from either end. However, let's look at the branches itself. This branch is a CH2, CH3, 2 carbons. So that's an ethyl. This branch here is 1 carbon, or consists of 1 carbon, so it's a methyl. So we have an M and an E for ethyl. In this case, go by the alphabet. Of course, as you know, we have A, B, C, D, E. So in this case, E for the ethyl, 2 carbons, comes before M for methyl. So in this case, we start numbering here because of the ethyl right here. So in this molecule, we have an ethyl and a methyl. So we list the ethyl first because E comes before M. And next we list the methyl here because M comes after E. Then we have to indicate the location of these groups. So the ethyl group is on carbon number 3, and here it is. And notice it's a dash to separate the number from the letter. And then the next group, the methyl group, is on carbon number 5, and here's the 5. And we separate a letter from a number with a dash, and a letter from a number from a letter using a dash. So we have 2 dashes around the 5 and a methyl heptane. So the name of this molecule, let me clear this up so we can see it. So the IUPAC name of this molecule here is 3-ethyl. Because why ethyl? Because that's a CH2, CH3, 2 carbons. 2 carbons represents is an ethyl. And a 5-methyl, here's a 5, and here's the methyl, CH3, and a heptane because the longest chain here has 7 carbons. So practice that. Here's another example. So let's see if we can give the IUPAC name of this molecule. Again, we'll use the line angle just to because that's how we'll communicate in chemistry, much easier. So we first find the longest chain. 1, 2, 3, 4, 5, 6. 6 carbons, hexane. Then we'll have to double check to make sure that we start numbering from the correct end, because we have the possibility of start numbering from here or from here. So here's a branch, and here's a branch. So yes, starting from here is correct and not from that end. So this will be the numbering that we'll use to come up with the IUPAC name. Okay, so let's see. On carbon number 2, we have a CH3 methyl and a CH3 methyl. And on carbon number 4, we have a CH2 and a CH3, which is an ethyl. So how do we name this molecule? We know that E comes before M. So we'll have to start with the ethyl. So it becomes a 4-ethyl. Then we know that M comes after, because that's methyl and methyl, and there are 2 of these. And they are on carbon number 2. So we say it's a 2-2. Notice we have to put 1 and 2 2's. Use 2 2's to represent this dimethyl right here. Dimethyl right here. So the IUPAC name now becomes 4-ethyl 2,2-dimethyl hexane. Why hexane? Because we have 6 carbons. what I should point out here is, notice this is an E and this is a D. Let me go back and clear this so you can see it. So notice this is an E and this is a D. So one may be asking, why don't we put dimethyl first, because D comes before E? And the answer is that the M is really the letter that determines the priority in naming. So this dimethyl or trimethyl or tetramethyl will not count towards the alphabet in terms of naming. It's just the E, here's the E, and the M. So since E comes before M, we start by naming it for ethyl and not 2,2-dimethyl. Okay, so let us look at this molecule here, and the question is, what is the IUPAC name of this molecule? So in other words, you have to give me the IUPAC name. So write that out. As you can see, this is part of the quiz or exam where you have to write out answers. So let's start. So we have 1, 2, 3, 4, 5. So that seems to be the longest chain. So we have a pentane as the longest chain. The question is, do we start here in our numbering or here? Since we have 2 methyls on the second carbon here, we will start at this carbon and not at this carbon, which just has 1 branch. So this becomes our longest chain, and we start at this carbon for numbering, and this is a branch, this is a branch, and this is a branch. So it has 3 branches. So we'll have to name those 3 branches. What I wanted to point out here again is that looking at these molecules, you will not just know the name. What we're asking you to do is apply what we have just learned to a molecule that you have not seen before, to naming a molecule that you have not seen before. So that's part of the training here in taking this course, is gaining some new knowledge, but equally important, can you apply that new knowledge to solving a problem that you have not seen before? So let's see if we can write the name of this molecule. So again, so what I would suggest is to number these. So 1, 2, 3, 4, 5. Pentane. We have a CH3 methyl, a CH3 methyl, and a CH3 methyl. So we have methyl, but we have 3 methyls, so it's a trimethyl. Notice if it's 3, it's going to be trimethyl. If it's 2, it's going to be dimethyl. So it's a trimethyl, and because we have 3 for trimethyl, we need 3 numbers back here to indicate the 3 carbons that these 3 methyl groups are on. And as you can see here, they are on carbons 2, so 2, 2, and 4. So 2, 2, 4, trimethyl pentane. So this would be the IUPAC name of this molecule. Okay, so once again, you should be able to look at a line angle structure and give the IUPAC name. Also, you should be able to look at the name, and you should be able to give the line angle structure. So once again, I'll emphasize, it's learning something new, but equally important, can you apply that knowledge to solving a problem that you have not seen before? And this is what we're trying to do here, is to expand your thinking as scientists. I think this is our last slide. Yes, it is. So what I want you guys to do is to continue working the problems in the book, in that chapter, and also I'll have a tutorial set coming out shortly over the weekend. Work those, and I'll say more in an email that I'll send to you. And remember, there's a quiz coming up on Thursday, the 28th of January, and we'll test your knowledge and how well you can apply what we have covered in this lecture, and of course in the past two lectures of the previous chapter, chapter 10. Okay, so continue to study hard and get ready for that quiz that's coming up on Thursday. Okay, bye.